In this video, I will solve question 5 from a practice questions for the final. So this one that's marked harder question, mixture of the first price and second price auctions. All right. So what do we have in this auction? We have a standard setting, standard canonical setting with two bidders, n equals 2, and the values are uniformly drawn from a distribution on 0, 100. Okay. And here's the auction. So we use this setting to solve first price auction. So let me remind you. So in class for first price auction, we figure out that the bidding function of a bidder in equilibrium will be to bid half of its value. And in second price auction, the bidder would bid using this function. So this is a truthful bidding function. You just literally take your value and you bid your value. Okay. In both of these auctions, we found that expected revenue was 100 over 3, 33.33. Okay, that's just a reminder for you. Now, in this question, in part A, we need to solve for mixed, this mixture of the first price auction and the second price auction. So what happens if basically the way it works, suppose bidder 1 bids 30 and bidder 2 bids 20, then bidder 1 would win, he will get the object, and he will pay the average of 2 bids. So he will pay 25. So it's neither first price auction, nor it's a fully second price auction. It's something in between. So this is the auction that we will be solving. So let me erase this. And so the technique we will use to solve this auction is same technique you used. I think it was problem set 7, the last question. Basically, it's a technique where instead of deriving optimal bidding strategy, you just trust revenue equivalence theorem and say, basically, I think this auction would also satisfy it. Therefore, this auction will generate an expectation exactly the same revenue as any of the standard auctions. And as a result, you have basically an easy way to figure out what the bidding function should be. Okay, so let's see how we can use it. Well, we'll start with second price auction, right? Well, we don't have to start with second price auction. We already have the revenue equivalence here. Let me change the marker. So let me remind you where it's coming from. So we have 0 to 100, and with two bidders, we slice it into 3 pieces. That will be 100 over 3, and this is 3. So this is one is the highest. This will be on average how much winner has. This is the lowest. This is on average how much the second bidder in terms of value. So, and that's why the revenue comes out exactly this amount, because in the second price auction, bidders would bid their value. On average, the highest bidder would be bidding 66.66, and on average, we expect the lowest bidder to bid 33.33. Therefore, revenue for the auctioneer will be 33.33. So now in this new auction, bidders, we will assume that bidders, so mixture, we will assume that bidders are using similar linear bidding functions. So they take their value and they multiply it by some kind of coefficient. Note that we do expect this coefficient to be less than 1 because the mixture is somewhere between these two things. Therefore, you don't have as much incentive to bid your true value, but it's also not that bad as a first price auction. So we think something, we should find something in between. So that would be my guess, just from this argument, that I will shade my value, but less than in the first price auction. All right, so now suppose both bidders use this bidding function, then it's very easy to calculate, even without knowing beta, it's very easy to calculate how much expected revenue this auction has. But then if we trust revenue equivalence, this thing has to be exactly this, and as for that will give us a way to get beta. So in the end, it's actually technically it's not a hard question, but it's very kind of theory heavy because you are using these nice tools. All right, so let's calculate expected revenue. And expected revenue will be So what the auctioneer does, it basically collects from the winner pays average of 2 bits. So the winner on average will have this value, and the second bit will be here, and the auctioneer will be collecting the average of these two values, and don't forget they will be multiplied by value. So what we have is 1/2, that will be the arithmetic average, b times minimum of v1, v2. Well, I mean, that will be, I guess, let's put expectation here, plus beta maximum, v1, v2. I don't have to write it that complicated, but let's write it this way. So that's my expected revenue that I will collect. So there will be a bidder with the lowest value, and his lowest value he will be beta of this, and that will be the second bid. And for the high bidder, it will be also beta times maximum value, and we take arithmetic average. So notice that for these expectations we have numbers, right? Therefore we will just plug them in. So we will have 1/2 beta times minimum will be at 100/3 plus beta, and the maximum will be on average here at 200/3. So let's just solve this. So we can take beta out, and we will have here 100/3 plus 200/3. That's just 300/3. This is just 100. Therefore, this is just 50 beta. Okay, and now we basically have the revenue of this weird auction as a function of beta. So it will generate 50 times beta, but then by revenue equivalence, 50 beta has to be equal to 100/3. So then the only way it could happen if beta is 2/3. And that's what we found. Notice it makes perfect sense because this is our bits in the first price auction, this is our bit in the second price auction, and this one we see somewhere in between. And I believe that we actually not only did part A, we might have, we might have did part B as well here. So let me, kind of don't like my markers today. So that was part A. Part B would have been, so let me erase all of this. So part B would have been a comparison, but we kind of already did it. So in the first price auction, we have function half V, this mixture. We have that one we derived, 2/3 V, and then second price is you're bidding your full value. So intuition is very simple. The more aggressive the price rule, the payment rule becomes, the more you shade your value. So if you pay your own bid, you shade a lot. If you pay somebody else value, you don't shade at all. You just bid your value. And when you are exposed to this average mixture of 1/2, 1/2, you're neither there nor you're here. So we expect you to bid somewhere in the middle. So that's the intuition. So that was part B effectively. So let's do part C now. So let me erase all of this. And for part C, we just need to redo part A with 3 bidders for n equals 3. So what I will do, I'll just complicate life for myself. I will actually do for generic, I will solve part C as if n is a parameter. So it can be 3, it can be 4, it can be 5, whatever. And then we can, in the end, we can just plug in and get the answer for n equals 3. But I think I'll get more mileage out of this way. Okay. Okay, so we will do Z for generic n. For generic n. So for this we need general order statistics. So remember this is 0, this is 100, and then our lowest value is 100/n+1, and it goes all the way to 100 times n/n+1. That's the highest order statistics, and the second highest will be 100 times n-1/n+1. That's the highest order statistics. So remember that basically if you have n draws from a uniform distribution on 0, 100, on average the highest will have value of this much, on average the second highest will have this value of this much, and so on. We only would need, I mean, the second one, then it basically goes like this. But for our purposes, we only need these two in auctions. We basically mostly can, usually we're exposed to these guys. This will be a third price auction, for example. In one of the problem sets, it showed up. Then you would use this sort of statistic for that. All right, so we need to figure out our generic auction. So again, so we'll start with second price auction. In second price auction, bidders bid their value. And expected revenue then is, if everyone bids their value, the highest bidder would bid its value, it will be here. The second highest bidder would bid its value, it will be approximately here. On average, it will be here. That's how much auctioneer will collect. So it's 100 n minus 1 over n plus 1. Now let's do mixture. So in a mixture, bidders bid some fraction of their value. We don't know what this fraction is, but we will just keep it as a parameter for now. Then our expected revenue will be what? Well, it will be arithmetic average of two things, right? The highest bidder will have this value, and he will bid beta of that value on average. So let's write it down. Plus, it will be arithmetic average of the second highest, because you take the winning bid, you take the next losing bid as the highest losing bid, and you averaged it out. And so that bidder on average would bid the second order statistic. Okay, so that's our revenue. So let's simplify it. So I'll take beta out. Let's keep beta, and let's actually also take 100 out. And then here we will have n over n plus 1 plus n minus 1, n plus 1. And yeah, let's just collect everything. So we'll have 100 beta 2 2n minus 1 over n plus 1. Okay, and now big finale. So we apply revenue equivalence. We say revenue equivalence must hold. Therefore, second price auction revenue should be equal to this one. Therefore, we just set it equals to 100 beta over 2 2n minus 1 over n plus 1. Okay, so you see 100 cancels out, n plus 1 cancels out. So what we're left with is n minus 1 beta over 2 2n minus 1. Okay, and then beta is simply what? So it's 2n minus 2 divided by 2n minus 1. All right, so we see that it's precisely, it's always less than 1, so you will never beat your value. It gets close to 1 as n grows, but you see that numerator is always slightly less than denominator. So for this particular, so let's check whether we did our job correctly. So let's plug in n equals 2 first. Then beta would have been 4 minus 2, 4 minus 1. That's 2/3. That's what we got in part A. So seems like it's working. And now I can plug it in for n equals 3. So that will be what? 6 minus 2, 6 minus 5. That's, oh, sorry, 6 minus 1. That's 4/5. I think it matches my my notes. Yeah, so but now notice that we solved it in general, so we can do n equals 10, for example. Then beta will be what? 18 over 19. So you see that coefficient gets very close to beating your true value. But that's also something expected. Even the first price auction, when you get a lot of bidders, you would start bidding very close to your value. So that makes sense. Okay, so that's how you solve question 5.